Welcome back. Today we're going to go through lesson 8.7, which is on graphing logarithmic functions. So first thing we need to remember is what the basic log function is. So the parent function of a log is y equals log base b, so that's a subscript of x. So then we can add transformations on that, just like we have done with other functions throughout the way. So when we transform it, we start with an a that we can multiply by that base of x. Remember that a can stretch or compress it. It can also reflect it. And then we can also shift it left or right based on how we transform the x value of the log. So we use the letter h to represent those horizontal shifts left and right. And then we can add a value on the end outside of the log that will shift our function up or down, and we use the letter k to represent that. Okay, so some key things that we need to remember when we're transforming our logs, that x minus h part of the function, in order for these logs to be functions, that has to be a positive number, so it has to be greater than 0. The base of our function also needs to be greater than 0, so a positive value. And then finally, the b value, that base cannot be equal to 1 in order for it to be a function. So we are going to explore these transformations in these log functions a little bit further here. So let's start with just these parent functions again. So on this graph, we kind of have two things going on that we need to talk about. So there's two graphs you can see. Only one of them represents the log. If you remember from previous lessons, the function above that diagonal line, that is the function b to the x. And for these two functions that we're looking at right now, our base value is greater than 1. So for a positive b value, when it was an exponential function, if you remember that from previous lessons, that's where it's exponential growth. So the log of that, or the inverse function of that, which we're going to explore more in a second, is this guy down here. So this is the parent function, log base b of x, right here, for b values that are greater than 1. Then on the other side here, we have the graphs for b values greater than 0, but smaller than 1. So decimals or fractions between 0 and 1. And in these cases, same idea. If you remember from exponentials, exponential decay is where that b value is less than 1. So it's getting smaller, closer to that asymptote at 0. So that is the exponential function. And then the log function is the opposite of that. So here is your log function, where the b value is less than 1 but greater than 0. So these two that I've kind of highlighted in color are the ones that we are looking at for log functions, but we're going to explore a little bit more about why we put those exponentials with them, because we should know at this point that exponentials and logs are inverses of each other. All right, so using those parent functions that I've highlighted there, let's talk a little bit about their end behavior. End behavior, remember, is what happens on the ends of the function. So for this first part, it says x is going to infinity, so that would be our right side here. That function, in this case, is getting closer and closer to infinity. It's going up and up and up. Even though it kind of looks like it's starting to flatten out, it will continue upward forever. And then on the left side, we can see that that function gets really, really close to 0, but it's never actually going to cross that 0. So our end behavior on logs is a little bit different. It's not negative infinity, it's only going to 0. And we'll talk about why that is in a second. But as that x value approaches 0, we can see that the function is pointing downwards, and it continues on downwards forever to negative infinity. Similar things happen on our logs where the b value is between 0 and 1. So in this case, we can see that as we go to infinity, our function down here is going further and further downward. So it's going to negative infinity. And then again, our function is going to approach 0. So it's getting closer and closer to that y-axis. It never actually touches it. And as that happens, our function is going upwards to infinity. So our end behavior is going up and down forever in this one. Okay, let's explore a couple more key features here. So in our parent function, remember that's our most basic function. before we transform it at all. So in this case, if you think back to exponential functions, we had horizontal asymptotes. Now we have vertical asymptotes. So the vertical asymptote, the vertical line that the function is getting closer and closer to in the parent function is 0, also known as our x-axis. And because of that vertical asymptote, that's stopping our domain. So in logarithmic functions, our domain stops at 0 and goes to infinity if it has no transformations on it. And the range this time, if we look up and down, it goes on forever. So it's going from negative infinity to positive infinity. And then for these functions, since they are restricted in their domain, we're going to actually focus on their x-intercepts because a lot of times they don't have y-intercepts. So the x-intercept for the parent function, if you think about a log, remember this is log base b of x. So if I'm looking for the x-intercept, I'm trying to figure out when will that log equal 0. And if we remember that logs are saying b to 0 power equals x in this case. So if we want to find that x-intercept, we know that anything to the 0 power is 1. So no matter what that base is, when I raise it to the 0 power, it's going to be 1. So my x-intercept is 1 in order to get out a 0 for my log. So those are the key features of the parent function, and then we start transforming it. So when we transform it, that vertical asymptote can only move left or right, and we know from our transformations up above that what moves it left or right is the h value in our equation. So whatever that h value is, that's where our vertical asymptote is going to be now. And when that vertical asymptote moves, that shifts the domain restriction. So our domain is going to go from h to infinity then. So wherever that asymptote moves to, our domain also moves to. The range in all these log functions is going to be negative infinity to positive infinity. No restrictions on that. And then our x-intercept in this case, remember from our transformations, the only thing that's going to change that x-intercept is going to be the a value. So our a value is going to help change the asymptote. Like I said, we were going to explore a little bit more about these log and exponential functions and why they're inverses of each other. So when we looked on the previous page, we could see that those graphs were inverses of each other. And we could see that they cross over that line, if you will, of y equals x that makes them inverses of each other. So we're just going to kind of algebraically prove here that they're inverses. So remember, we can use composition, and if we can get out the value of x, that proves that they're inverses. So we're going to use our properties of logs and our properties of exponents to kind of help us here. So first we have to compose f of g of x. So that means we're going to take g of x, which is the log base b of x, and plug it in for the variable here. So that would look like b to the log base b of x power. And we know from the exponential logarithmic inverse property that when that happens, the log of b and base b cancel each other out, and that x becomes your answer, no longer as an exponent. So again, because of that exponential logarithmic inverse property, we know that those undo each other basically, and the x drops out of the exponent to leave us with just itself. Then we also have to prove it in the inverse way. So now into log base b of x, we have to plug b to the x power. And when we do that, using that same property, that exponential logarithmic inverse property, we know that rewriting this, we have b to some power has to equal b to the x. And the only thing that can go in that spot is x. So same thing, as long as we get x out, we can see that both of them equal x, and that tells me that they are inverse functions of each other. So that's just a little side note to help us remember why they're inverses of each other and how that changes our graphs. So we're going to practice a little bit with the graphs here. So we're going to start by graphing from a table, or using a table to kind of help us. So for example A here, we have 2 times log base 4 of x. So in this function, the first thing that I am going to look for is where the asymptote is going to go. Remember, it's a vertical asymptote, and the only thing that would affect it is a horizontal shift left or right. If I look at my x in my equation, it has no shift. So that means that my asymptote stays at x equals 0. So I always kind of draw that on my graph to help me know where my function's stopping. When that asymptote stays at 0, that means that my domain also stays at 0. So I can fill that in to help me. And we should hopefully remember that the range is not going to change on these functions. So it's negative infinity to positive infinity. All right, so the last piece we're missing here is the x-intercept. So we want to figure out what is going to make my function equal 0. We should know that all our x-intercepts have a y value of 0. So I'm trying to figure out what would make this function equal 0. And I'm actually going to do this over under the function here. So I'm trying to figure out what would make this function equal 0. Now, if you're allowed to use a calculator, you're certainly allowed to graph these and find the x-intercept that way, and we'll talk about that more on the next problem. But if you have to find it algebraically, we can say that, all right, if we want 2 times the log base 4 of x to equal 0, then 0 has to equal the log base 4 of x because of our multiplication properties. So if we rewrite that in exponential, that's 4 to the 0 power equals x, and we know that 4 to the 0 power is 1. So that tells me that my x-intercept is at 1 in order to get a 0 out. Right. So we know our x-intercept is here at 1. So I'm going to fill that in my table and then find some more numbers to go with it. So based on my graph, I know that I'm going to look for numbers to the right of 1 because I have that asymptote as 0. So I'm going to find 2, 3, 4, and 5 to complete my graph. So again, you can use a calculator or you can figure some of them out in your head. Some of them you're going to need a calculator to kind of help you. So when I plug in a 2, I get out a 2. When I plug in a 3, I get about 1.59. Again, using my calculator, 2 times log base 4 of whatever number I'm plugging in. When I plug in 4, that one I could do in my head. Log base 4 of 4, that's 1 times 2 is 2. And then when I plug in 5 for x, I get about 2.32. So I can plot these points on my graph here and start to get an idea of what's going on here. And I just realized I messed that 2 up. Sorry about that. So if I plug in 2, that's a half. Half of 2 is 1, so that should be 1. So 2, it's at 1. 3 gets a little bit higher. 4 a little higher. So you can kind of see that curve starting to happen here. So again, we know with our asymptote, we're going to approach it, get really, really close, but not touch it, and then grow from there. Okay, let's go ahead and look at another one here. So for b here, we have log, remember there's no base, that means that the base is 10 of x plus 1 minus 4. So I see this plus 1 in the parentheses with x. That tells me that there is a shift left 1, which means my asymptote is now going to be at negative 1. So I'm going to draw that on my graph to start with. And then, of course, we know that the asymptote affects the domain. So my graph is now going to go from negative 1 to infinity, and my range is going to stay the same. And then again, we have to find that asymptote. So you can start to kind of figure out algebraically what this looks like. So I can move, so I want to figure out when it equals 0. I can move the 4 over. And then I kind of get to this place here when I rewrite it in exponential form. I get 10 to the 4th power, which is 10,000. And then when I subtract that 1 over, I get 9,999. You can also find that again on the graph. Graph log of x plus 1 minus 4, graph y equals 0. Find their intersection point. So my x-intercept on this one is at 9,999, 0. So obviously not going to fit on our graph here, but we can start to get some ideas. So I know, again, kind of where my asymptote is. So I'm going to start with an x value of 0. Because that's the first whole number exponent, or whole number x value that I can plug in besides my asymptote. So when I plug in 0, I'm going to get out a negative 4. when I plug in, and I'm just going to go from there. So when I plug in a 1, I'm going to get out a negative 3.7 about, which again, I'm using my calculator to find. When I plug in a 2, I get out negative 3.5. When I plug in 3, I get negative 3.4. When I plug in 4, I get negative 3.3. So we can get an idea of kind of what our graph is looking like here. We know it gets a little bit higher each time we move over. So again, it's approaching that asymptote, getting really, really close, and then curving from there. All right, we're going to continue graphing here, but now rather than given the whole equation, we're going to use our transformations to help us a little bit here. There we go. All right, so our equation on this one is log base 2 of x minus 2. So I can see the transformation that's happening here is that it is shifted right 2. So translated right 2. That means, remember that my asymptote is now at positive 2. So y equals 2 is my asymptote. Or sorry, x equals 2. It is a vertical asymptote, so going through x equals 2. And then, again, I can start to kind of figure out where my x-intercept is by plugging in 0 for y. So we have log base 2 of x minus 2. So that means that 2 to the 0 power has to equal x minus 2. Anything to 0 power is 1. And when I add that 2 to both sides, I get an x-intercept of 3. So there's my x-intercept. I know for my asymptote that my domain now goes from 2 to infinity, and my range is negative infinity to positive infinity. All right, so based on those transformations, since we're not using a table this time, we're just kind of guesstimating with our key points that we know here. So I know it's going to go through there, and it's down here, comes up, and curves. All right, and then our final one based on transformations here, I can see 2 transformations going on. We've got a shift left or a translation left 3. And then we also have a translation vertically going up 5 because of that plus 5. All right, so that shift left 3 tells me that my asymptote is now at negative 3. So I'm going to draw that on my graph here. That tells me my domain is now negative 3 to infinity. My range, of course, is negative infinity to positive infinity. All right, let's see if we can find that x-intercept now. So plugging in 0, we're trying to figure out what x value would give me that. So we're going to get negative 5 equals log of x plus 3. So that's 10 to the negative 5 power equals x plus 3. And when we do 10 to the negative 5 power, we get 1 over 100,000 equals x plus 3. So essentially we have a tiny, tiny decimal, 1 over 100,000, really small number. So when I subtract 3 from both sides, I essentially get negative 2.99999. So very, very close to that asymptote of 3, but not quite there. So my asymptote is really, really close to that, or my intercept is really, really close to my asymptote, but obviously doesn't actually touch it. We also know from this one that it's translated up 5, so that means that my curve is kind of coming in a little bit higher and then dropping down really close there. So it looks something like that using the transformations to graph. All right, we are going to write the function given the parent function and a graph, so we can kind of start to see what's going on from the graph, and then based on the parent function, what we need to write. All right, so when I look at this function, it looks like the asymptote is still at 0. So I know that my transformations don't have any horizontal translations. So that asymptote is still at 0. That means my domain is still 0 to infinity, and my range is negative infinity to positive infinity. So what we have to figure out now is where that x-intercept is. So looking at the graph, I can tell it's close to 0, but I can't see exactly what it is. So what I am going to do to kind of figure out what's going on here is I'm going to find another key point that I can easily see. So on my graph, I can see this point. I can see this point that is at 1, 1, 4. So that is going to be a key point to kind of help me figure out what is going on here. So what I know from this parent function, if I plug in a 1 to my parent function for x, because I know that point has an x value of 1, if I plug that in, I know that I should get out a 0 from my log. But what we know from the graph is that it's actually at 4. So that means that the y value should be down here at 0, but it has moved up to 4. So that means that I have a translation up 4 going on here. And because of that translation, I know that my function is not just log base 2 of x, but it has a plus 4 on the end to make that vertical translation happen. Once I know that, then I can find my x-intercept. So remember, we're trying to figure out what would make this function equal 0. So when we subtract the 4, we get a negative 4 of log base 2 of x. That means we have 2 to the negative 4 power for our x-intercept, which is 1 over 16. So once we know the transformations, then we can go back and find our x-intercept based on what's going on, since we can't see it clearly on the graph. All right, let's look at one last example here. So in this function, we have the parent function log of x, and we have our graph going on here. So I can see from my graph that my asymptote appears to be at 5. So that means my domain is 5 to infinity, and my range, of course, is negative infinity to positive infinity. All right, so I know from that asymptote that it has translated right to 5. So we're going to use that to kind of help us here. So again, I'm going to kind of look for a key point that's going on here. So in this one, I can see that I have a key point of 6, negative 2. So I'm going to use that to kind of help me figure out what's going on with the rest of my transformations that I might need to find. So we already know our one transformation is right 5. So I know right now that the bare minimum my function has is x minus 5 because of that transformation that I can see in the asymptote. So if I plug in 6 to my function here, that means that I get the log of 1. So again, that means that I am looking at 10 to what power equals 1. And I know that that has to be 0. So what that means right now is that when I plugged in a 6, I got out a 0. But we know from our graph that that point is actually at 6, negative 2. So that tells me that to go from 0 to negative 2, I would have had to shift my function down 2. So that means that my equation also has a shift down 2. So my final equation with those transformations in it is log of x minus 5 for the shift right 5, and then minus 2 on the end to get that vertical transformation down 2. All right, once we know that, then we can figure out what the x-intercept is. So if I want my function to equal 0, that means that when I solve, I add 2 to both sides. Log of x minus 5, so that's 10 squared equals x minus 5, so that's 100 equals x minus 5, so x must be 105 for my intercept. All right, that's all for today. See you next time.